There's something mesmerizing about looking up at the night sky, knowing that every pinprick of light is a story, a mystery waiting to be unraveled. But some of those stories are stranger than fiction, and few places in the cosmos embody that strangeness quite like the Antennae Galaxies. Picture this: two massive galaxies, locked in a slow-motion collision that's been playing out for hundreds of millions of years. In this cosmic dance, stars are born and die in spectacular explosions, while gravity twists and distorts entire regions into mind-bending shapes. The result, a celestial laboratory where the ordinary laws of physics seem to bend, and the unexpected becomes routine. What makes the Antennae Galaxies so fascinating isn't just their dramatic collision. It's the sheer number of bizarre phenomena packed into one swirling, chaotic scene. From black holes behaving in ways we can't yet explain to vast clouds of gas glowing with energies we've never seen before, this is a place where the universe feels like it's showing off. And today, we're diving deep into 25 of the most bewildering, awe-inspiring, and downright strange occurrences happening right now in this distant corner of space. These aren't just scientific footnotes, they're cosmic puzzles that could redefine how we understand everything from star formation to the very fabric of reality. So why should you care about two galaxies colliding billions of light years away? Because hidden in their chaos are clues to some of the biggest questions we've ever asked. How do galaxies evolve? What happens when titanic forces warp space and time? And could the answers to these questions change our understanding of the universe itself? This isn't just a tour of celestial oddities, it's a front-row seat to the kind of discoveries that remind us just how little we truly know. Buckle up, because by the end of this journey, you'll never look at the night sky the same way again. Among the most striking features of the Antennae Galaxies are the colossal starburst regions, cosmic nurseries where new stars ignite in a frenzy of creation. Imagine entire swaths of space, each spanning thousands of light years, lighting up with thousands of newborn stars in just a few million years. That's an astronomical blink of an eye. These regions aren't just productive, they're downright explosive, producing stars at rates hundreds of times faster than anything we see in our own Milky Way. What's fueling this frenzy? The answer lies in the galactic collision itself. As the two galaxies smash together, gravity twists and compresses their vast clouds of gas and dust, squeezing them until they collapse under their own weight. It's like crumpling a sheet of paper, only instead of wrinkles, you get towering pillars of glowing gas where stars burst to life. The result is a fireworks show on a cosmic scale, with massive, brilliant stars forming in dense clusters so packed together they outshine entire sections of the galaxies. But these starburst regions aren't just spectacular, they're also incredibly violent. The most massive stars burn through their fuel in just a few million years, ending their lives in devastating supernova explosions. These blasts churn the surrounding gas, triggering even more star formation in a chain reaction that keeps the cycle going. Scientists study these chaotic nurseries because they offer a rare glimpse into how the first galaxies might have formed billions of years ago, when the universe was young and raw with energy. And here's the twist: while starbursts are common in colliding galaxies, the Antennae Galaxies take it to another level. Some of these regions shine so brightly in infrared light that they rival quasars, the most luminous objects in the universe. That's because the dust from all this star formation absorbs visible light and re-radiates it as heat, turning these areas into blazing beacons that defy expectations. It's a reminder that even in the cold depths of space, chaos can create beauty, and that the universe still has plenty of surprises left to reveal. Deep within the turbulent cores of the Antennae Galaxies, something extraordinary is unfolding. A gravitational tango between two supermassive black holes, each weighing millions of times more than our Sun. As these cosmic behemoths spiral ever closer, locked in a fateful embrace by their mutual pull, they're rewriting the rules of physics in real time. Their dance isn't silent, though. With every orbit, they ripple the fabric of space-time itself, sending out gravitational waves that echo across the universe. These waves aren't just faint whispers, they're monumental distortions in space, generated as the black holes whip around each other at blistering speeds, warping everything in their vicinity. Imagine tossing a pebble into a pond, but instead of water, the ripples twist the very dimensions of reality. Scientists detect these waves with observatories like LIGO and Virgo, but the signals from the Antennae Galaxies are a preview of something far more dramatic. A collision that will one day merge these two giants into a single, even more monstrous black hole. What happens when they finally collide? The energy released will be unimaginable, outshining every star in the galaxies combined as it's funneled into those gravitational waves. For a brief moment, this merger could become the brightest event in the observable universe, a flash of raw power that would redefine our understanding of black hole dynamics. Yet the aftermath is just as fascinating. The newborn supermassive black hole will recoil from the violent union, possibly even getting kicked out of the galactic center entirely, sent careening through its surroundings like a cosmic pinball. But here's the real mystery: why hasn't this merger happened already? Despite their closeness, the black holes seem to be stuck in a slow-motion waltz, held apart by the sheer amount of gas and stars swirling between them. It's a cosmic traffic jam on the grandest scale, where chaotic forces keep them dancing for now but not forever. When the final plunge comes, it won't just reshape the Antennae Galaxies. It'll give us front-row seats to one of the universe's most extreme events, a spectacle that could unlock secrets about how galaxies grow and how black holes rule them. This isn't just theoretical either. Similar mergers have been detected across the cosmos, but witnessing one so close, relatively speaking, could provide unprecedented details. Will their collision fling stars into deep space? Could it trigger another wave of star formation? Every observation brings us closer to answers, turning these two dueling black holes into a living laboratory for the most extreme physics in existence. One thing's certain: their dance is far from over, and every step holds a new revelation. The Antennae Galaxies hold more than meets the eye, literally. Wrapped around their spectacular collision is an invisible cloak of dark matter, its presence felt only through the gravitational fingerprints it leaves behind. Picture an enormous, unseen hand sculpting the galaxies from the shadows, bending streams of stars and gas into peculiar shapes as if space itself were made of taffy. This dark matter halo isn't just a passive bystander, it's the hidden architect of the entire collision, dictating how fast the galaxies merge, where stars form, and even how violently they'll eventually settle into one. Dark matter's influence becomes clear when you notice something odd. The visible material, stars, gas, and dust, doesn't account for the way the Antennae Galaxies move. Their outer regions rotate too quickly, their gravity too strong for what we can see. That discrepancy points to an invisible mass, a gravitational glue holding everything together. Without it, the galaxies would have flown apart long ago. Instead, their dark matter halos intertwine like ghostly webs, creating a scaffold that channels the chaos of the collision into something almost orderly. But here's where it gets stranger. As the galaxies plunge through each other, their dark matter doesn't collide or slow down like normal matter does. Gas clouds smash together, triggering star formation, while stars themselves rarely hit one another. But the dark matter, it just passes right through, barely interacting at all. This creates a bizarre mismatch. The luminous parts of the galaxies lag behind, twisted and stretched by friction, while their dark matter halos surge ahead, pulling the visible material along like an invisible leash. Scientists study this dance because it's one of the clearest windows into dark matter's behavior. The Antennae's violent merger lets us map where dark matter clumps by watching how it bends light from background galaxies, a phenomenon called gravitational lensing. These distortions reveal dense pockets of invisible mass, some so large they defy current theories. Could there be dark matter structures we've never predicted? The antennae might hold the answer, and then there's the ultimate question: what happens to dark matter after the merger? Some models suggest the halos will eventually merge into one, while others predict a turbulent mix that never fully settles. The outcome could reshape our understanding of how galaxies evolve, hinting at whether dark matter is cold and slow-moving or warm and more dynamic. Every observation of the antennae adds another clue, turning this cosmic wreck into a laboratory for the universe's greatest mystery. One thing's certain: without dark matter, the Antennae Galaxies wouldn't just look different, they might not exist at all. Its invisible hand doesn't just shape this collision, it's the reason galaxies can form in the first place. So while we can't see it, touch it, or even detect it directly, its gravitational symphony is the unseen force conducting one of space's most spectacular shows. Stretching like cosmic bridges between the colliding Antennae Galaxies, vast filaments of gas twist and ripple across thousands of light years, tendrils so massive they could wrap around our Milky Way multiple times. These aren't just random strands of cosmic debris, they're the scars of a gravitational tug of war formed as tidal forces ripped gas from the galaxies during their close encounters. Picture two whirlpools passing near each other in a vast ocean, each pulling water from the other into long, arcing streams. Now replace water with superheated hydrogen, and you've got a glimpse of this otherworldly spectacle. What makes these filaments so extraordinary isn't just their size, it's their role as galactic lifelines. Packed with enough raw material to birth millions of stars, these rivers of gas act as cosmic conveyor belts, funneling fuel into regions where gravity will eventually sculpt new stellar nurseries. Unlike the chaotic starburst zones nearer the galactic cores, these filaments are quieter, slower incubators, places where star formation unfolds over eons rather than in explosive bursts. But their calm belies their importance. Without them, the Antennae Galaxies would lose vast reservoirs of the very stuff that builds stars, planets, and potentially even life. Scientists study these structures like forensic investigators, reading their shapes for clues about the collision's history. The filaments' intricate knots and loops reveal the exact moments when the galaxies grazed past each other, their gravity stretching gas like taffy. Some strands even glow with the faint echoes of ancient supernova, evidence that earlier generations of stars lived and died here, seeding the gas with heavy elements essential for forming rocky worlds. It's a fossil record written in hydrogen, one that tells us galactic mergers don't just destroy, they redistribute, recycle, and reignite. But the real surprise: these filaments might hold the key to a cosmic mystery: how galaxies avoid running out of gas. Normally, star formation would deplete a galaxy's fuel over time, yet the antennae's filaments show how collisions can replenish it, dredging up gas that might otherwise have remained dormant. In a way, they're the universe's version of sustainable development, proof that even violent encounters can birth new opportunities. And here's the twist: some of these filaments are far colder than theories predicted. While most of the gas is scorching hot, certain regions have cooled enough for molecules to form, creating pockets where future star birth could unfold under conditions eerily similar to those in our own galactic neighborhood. That's raised tantalizing questions. Could planets someday form in these isolated ribbons, far from any galaxy's center? It's a reminder that even in the most hostile environments, the universe finds ways to craft the ingredients for new beginnings. As telescopes peer deeper into these structures, they're uncovering another layer of complexity: magnetic fields threading through the gas like invisible wires, guiding its flow and potentially steering where new stars ignite. These fields might explain why some filaments resist dissolving into the void, holding their shape against the chaos of the collision. It's a delicate balance, one that showcases how gravity, magnetism, and turbulence conspire to shape the cosmos on scales we're only beginning to comprehend. So the next time you gaze at the Antennae Galaxies, remember, those faint, wispy bridges between them aren't just aftermath. They're blueprints for the future, silent architects crafting the next chapter in a story that began hundreds of millions of years ago. And somewhere in their shimmering depths, the seeds of tomorrow's stars, and perhaps tomorrow's worlds, are already taking shape. Hidden within the chaos of the Antennae Galaxies collision, there's a celestial exodus underway, stars being flung into the void at speeds so staggering they defy belief. These aren't your average stars drifting lazily through space. These are hypervelocity escapees, cosmic projectiles launched by gravitational slingshots with enough force to break free from their galactic homes entirely. Some reach velocities exceeding 2 million miles per hour, so fast they could cross the distance from Earth to the Moon in under 15 minutes, the culprit behind this stellar catapult. The relentless gravitational tug of war between the two merging galaxies. As their cores swing past each other, the combined pull of billions of stars and dark matter creates chaotic tides. Think of a whirlpool flinging debris outward with violent spins. When a star happens to pass too close to the supermassive black holes at the galaxy's hearts, it doesn't just get a speed boost, it's hurled outward like a pebble from a child's slingshot, only on a scale where the pebble is a blazing sphere of plasma larger than our sun. But here's what's even wilder. Some of these stars aren't just escaping their galaxies, they're on trajectories that'll send them hurtling into intergalactic space forever. Without the pull of a galactic anchor, they'll drift through the cold, empty vastness between galaxy clusters, their light fading into darkness over eons. Astronomers call them rogue stars, and their isolation raises eerie questions. Could planets orbit these lone wanderers? If so, their night skies would be nearly starless, just an eternal black canvas punctuated by the faint glow of distant galaxies, a far cry from our own star-studded view. Tracking these stellar fugitives isn't just about spectacle. It's a way to map the invisible forces shaping the collision. By tracing their paths backward, scientists can pinpoint exactly where and when the galaxy's gravitational forces were most violent, like forensic astronomers reconstructing a cosmic crime scene. Some hypervelocity stars even carry chemical signatures in their light clues that reveal they were torn from dense star clusters near the galactic centers, places where stellar encounters are as frequent as they are brutal. Yet the Antennae Galaxies aren't the only place this happens. Similar hypervelocity stars have been spotted streaking through our own Milky Way, likely ejected by its central black hole. But what makes the Antennae's case unique is the sheer scale of the phenomenon. With two black holes dueling in the chaos, the rate of stellar ejections could be 10 times higher than in isolated galaxies, creating a veritable highway of rogue stars racing into the void. And then there's the lingering mystery. What becomes of these castaways? Over billions of years, a handful might be captured by other galaxies, adopted into new stellar families. Others could collide with interstellar gas, igniting brief but brilliant shockwaves visible across the cosmos. Most, though, will simply fade into obscurity, ghosts of a galactic collision that happened long before Earth even existed. Their existence is a reminder that the universe is anything but static. Even stars, those seemingly eternal beacons, can be uprooted by forces beyond comprehension, set adrift on journeys that span eternity. So the next time you look up at the night sky, remember, somewhere out there, a star born in the Antennae Galaxies is racing through the darkness, carrying with it the untold story of a collision written in the stars. Beyond the visible chaos of the Antennae Galaxies, something invisible yet colossal stretches into the darkness, vast, ghostly lobes of radio waves extending hundreds of thousands of light years into intergalactic space. These structures aren't just leftovers from the collision, they are active energy highways channeling power from the galaxy's supermassive black holes into the cosmic void. Picture a pair of enormous loudspeakers in space, except instead of sound, they're blasting out jets of particles moving near the speed of light, lighting up the surrounding gas like a neon sign in the universe's darkness. What creates these radio lobes? The answer lies in the frenetic activity around the twin black holes. As matter spirals toward them, violent magnetic fields and friction heat it to millions of degrees, launching jets of charged particles into space. These jets plow through the sparse gas between the galaxies, creating shock waves that excite the surrounding material and make it glow at radio frequencies. The lobes we see are essentially the footprints of these jets' staggeringly large bubbles of energy, marking where black hole fury meets the quiet of intergalactic space. But here's where it gets even more intriguing. The antennae's radio lobes aren't symmetrical. They're twisted, warped, and fragmented, telling a story of turbulence we rarely witness elsewhere. Normally, such jets shoot out in straight lines, but the galaxy's collision has turned their environment into a gravitational obstacle course. Gas clouds, tidal forces, and even the black hole's own orbital motion bend and distort the jets, sculpting them into shapes that resemble cosmic spaghetti. This messiness is a goldmine for astronomers. By studying the lobe's kinks and bubbles, they can reconstruct the history of the merger itself, almost like reading tree rings to learn about Earth's past climate. The scale of energy involved is almost beyond comprehension. The particles in these lobes carry enough power to outshine entire galaxies for brief moments, yet they're so diffuse that they'd barely warm your hand if you could stand inside one. That paradox, extreme energy spread thinly across vast distances, is what makes them so fascinating. They act like cosmic pressure valves, releasing the black hole's excess energy without disrupting the delicate dance of star formation elsewhere in the galaxies. And then there's the longevity question. Unlike starbursts or supernova, which flare and fade quickly, these radio lobes persist for millions of years, evolving as the merger progresses. Some sections may collapse under their own weight, while others expand until they dissipate into the void. The particles within them will eventually slow down, their energy fading into the background hum of the universe, but not before leaving behind a fossil record of magnetic fields and heated gas that future astronomers might study to understand this moment in cosmic history. What's most surprising, though, is how common these structures might be. Nearly every galaxy merger shows some form of radio emission, but the antennae's lobes stand out for their complexity. They're not just relics of black hole activity, they're also redistributing energy and heavy elements far beyond the galaxy's original boundaries. In a way, they're galactic recycling plants, taking the ashes of devoured stars and spreading them across intergalactic space, seeding future generations of stars and planets with the building blocks of everything from rocky worlds to living organisms. So while the antennae's collision will eventually fade and the galaxies will merge into one, these radio lobes may outlast them all, fading into whispers of radio static over billions of years. They're reminders that even the most violent cosmic events leave echoes, and those echoes might someday help us understand how every galaxy, including our own, came to be. Among the most violent and energetic phenomena in the Antennae Galaxies, there's a silent epidemic unfolding, a dramatic spike in X-ray binary systems, where black holes and neutron stars strip material from companion stars in a deadly cosmic embrace. These aren't just random pairings, they're direct products of the galactic collision, their numbers surging as the chaos of the merger reshapes the destiny of countless stars. The reason behind this surge lies in the collision's aftermath. As the two galaxies intertwine, their gravitational dance flings stars into chaotic new orbits, forcing close encounters that would never happen under normal circumstances. Imagine a crowded ballroom where dancers suddenly change partners in unpredictable ways, except here, the dancers are massive stars, and a misstep means one gets torn apart by its neighbor's gravity. The result, a dramatic rise in binary systems where a compact, dense remnant, a black hole or neutron star, orbits a normal star close enough to steal its material. As this stolen gas spirals toward the black hole or neutron star, it heats up to millions of degrees, glowing fiercely in X-rays. These X-ray binaries become some of the brightest beacons in the galactic wreckage, outshining entire star clusters in high-energy light. But what's truly astonishing is their sheer quantity. The Antennae Galaxies host hundreds of these systems, far more than typical galaxies of their size. That excess tells scientists something profound. Galactic collisions don't just birth new stars, they also forge the perfect conditions for stellar cannibalism on a massive scale. The link between these X-ray binaries and the collision's starburst regions is crucial. The same gas compression that triggers frenzied star formation also increases the chances of massive stars forming in tight pairs. These stars live fast and die young, with the more massive partner collapsing into a black hole or neutron star long before its companion expires. Then, as the merger stirs the galactic pot, gravitational nudges shrink their orbits until the feeding begins. It's a chain reaction. More massive stars mean more remnants, and more remnants mean more X-ray binaries lighting up the chaos. But some of these systems defy expectations. A handful of the Antennae's X-ray binaries shine hundreds of times brighter than theory predicts, as if the black holes or neutron stars are gorging themselves beyond sustainable limits. One explanation: the collision's dense environments might allow multiple stars to interact simultaneously, funneling extra material into the voracious compact objects. Picture a star not just being siphoned by one black hole, but bullied by several nearby remnants, its outer layers ripped away from multiple directions. The result would be a feeding frenzy visible across the universe. What makes these systems more than just cosmic oddities is their role as dark matter detectors. As black holes and neutron stars accrete material, their X-ray emissions flicker in ways that reveal their masses, and some weigh significantly more than isolated remnants in common galaxies. That extra heft might come from dark matter particles getting trapped in their gravity wells and annihilating, releasing energy that subtly alters the system's behavior. If confirmed, this would give astronomers an entirely new way to study dark matter's distribution in colliding galaxies. Yet the most intriguing question remains: what happens to these binaries as the merger progresses? Some will be torn apart by further gravitational encounters, their stellar components flung into the void. Others might spiral closer until they merge, producing gravitational waves we could detect. And a few could survive for billions of years, becoming fossils of this cosmic collision long after the galaxies have settled into one. Each outcome offers clues about how such violent events shape the universe's population of black holes and neutron stars, and how often they might light up the darkness with their deadly feasts. The most iconic features of the Antennae Galaxies stretch far beyond their merging cores, two colossal tidal tails arcing through space like cosmic ribbons, each spanning over 300,000 light-years. These breathtaking streams of stars and gas didn't just earn the galaxies their name, they tell the story of the collision itself, acting as a celestial fingerprint of the gravitational forces that shaped them. Picture two galaxies passing so close that their mutual gravity acts like a tidal wave, pulling stars and gas outward in opposite directions. What remains are these shimmering trails, filled with the debris of a cosmic near-miss that happened millions of years ago. What's astonishing about these tidal tails isn't just their size, it's what's happening inside them. Unlike the chaotic cores where star formation runs rampant, the tails host a more orderly but no less spectacular phenomenon: vast clusters of young blue stars, some only a few million years old, gleaming against the darkness. These stellar nurseries form as gas compressed during the collision collapses under its own gravity, igniting new stars in isolation from the galactic centers. The result is a paradox: regions of serene beauty born from one of the universe's most violent events. Scientists study these tales like pages in a history book. Their curvature reveals the angle and speed of the galaxy's initial encounter, while the distribution of star clusters hints at how gas behaves when stretched to its limits. Some clusters are so dense they resemble miniature galaxies, bound together by gravity and destined to orbit the merged antennae for billions of years. Others are more fragile, their stars already beginning to drift apart, leaving behind glowing streams that will eventually fade into the void. But the real surprise lies in the tail's chemistry. Spectroscopic observations show they're laced with complex molecules, carbon monoxide, water, and even organic compounds, suggesting these remote regions could someday birth planets. That raises a tantalizing possibility. Could life arise in the tidal tails of colliding galaxies, far from the safety of a galactic disk? While it's a long shot, the presence of these molecules proves the universe is efficient at scattering life's ingredients even in the most unexpected places. The tails are also cosmic recycling plants. As they sweep through intergalactic space, they collect stray hydrogen atoms, funneling this primordial fuel back toward the merger. Over time, some of this gas may fall into the newly formed galaxy, providing raw material for future stars. It's a reminder that nothing in the universe is truly wasted. What's torn apart can be rebuilt, often into something even more remarkable. Yet the tails won't last forever. Over billions of years, gravity will stretch them thinner, their stars dispersing into the wider universe. Some may become part of a future galactic halo, while others could be captured by passing galaxies. But for now, they stand as luminous monuments to the collision, their glow a testament to the forces that shaped them. The Antennae Galaxies may eventually merge into a single elliptical galaxy, but these tidal tails will linger as the final echoes of a dance that began before Earth existed. A reminder that even destruction can create beauty on a cosmic scale. Scattered throughout the Antennae Galaxies like cosmic shadows, there are regions so dense and dark they swallow starlight whole. Vast clouds of gas and dust that don't glow, reflect, or reveal anything. These aren't your typical nebulae, they're something far stranger. Pitch-black clumps where temperatures plunge near absolute zero, and gravity pulls material together in eerie silence. While most of the collision's chaos blazes with light, these ghostly patches lurk unseen, detectable only when they blot out the stars behind them like celestial ink stains. What makes these dark clumps so puzzling isn't just their ability to hide. It's the way they defy expectations. In most galaxies, dense gas clouds light up when new stars ignite inside them, their dust grains reflecting or re-radiating energy. But here, some regions remain stubbornly dark, absorbing even the intense radiation from nearby starbursts without so much as a flicker. It's as if the universe has carved out pockets of pure void, places where matter huddles so tightly that light simply vanishes. Scientists believe these clumps could be cosmic cocoons, places where star formation is happening, but so deeply embedded in dust that no signal escapes. Imagine a fireworks factory wrapped in layers of thick wool. The explosions might be spectacular inside, but from the outside you'd never know. The sheer density of these clouds suggests they're not just passive obstacles, they're likely cradles for massive, hidden star clusters. They're stellar newborns smothered under blankets of debris until they grow powerful enough to blow their dusty shrouds apart. The origins of these dark behemoths trace back to the collision itself. As the galaxies grazed past each other, shockwaves compressed loose gas into knots hundreds of times denser than typical interstellar clouds. Some may even be the remnants of shredded molecular clouds from the galaxy's original structures, crumpled and compacted by tidal forces until they became nearly opaque. Others might be accumulating fresh material as they plow through the merger's chaos, growing darker and heavier with every passing million years. And here's where it gets truly strange. Certain clumps appear to be failed stars on a galactic scale, regions where gravity almost but not quite won the battle to ignite nuclear fusion. Had they been slightly denser, they might have collapsed into supermassive stars or even black holes. Instead, they linger in limbo, too cold to shine but too massive to disperse. challenging our understanding of how star formation thresholds work in extreme environments. There's another twist: these clumps might be hiding more than just stars. Radio telescopes have detected faint whispers of complex molecules like methanol and formaldehyde deep within their depths, hinting at chemical factories operating in the darkness. In the frigid void between dust grains, atoms could be linking into probiotic compounds, the very building blocks of life, shielded from the destructive radiation outside. It's a tantalizing thought. Could the antennae's darkest corners be brewing the ingredients for life while bathed in perpetual night? Unraveling this mystery requires more than visible light. Astronomers peer through the gloom using infrared and radio wavelengths, where heat signatures and molecular vibrations betray the clump's secrets. Some reveal telltale glows, evidence of buried protostars heating their surroundings from within. Others show bizarre substructures, filaments, knots, and even spiraling patterns that suggest magnetic fields are shaping their evolution in ways we don't yet understand. What's certain is that these dark clumps play a critical role in the antennae's evolution. By locking away vast reserves of gas, they regulate how quickly stars can form, effectively putting a brake on the merger's most violent bursts of creation. They might also serve as galactic warehouses, preserving raw material for future star formation long after the collision's initial fireworks fade. As telescopes grow more sensitive, we're catching glimpses of their true influence, not just as cosmic shadow puppets, but as architects of the galaxy's future. One day, they'll either dissolve under the pressure of newborn stars or collapse into the next generation of stellar giants. Until then, they remain some of the universe's most enigmatic hideouts, proving that even in a spectacle as bright as colliding galaxies, darkness still holds its deepest secrets. Beneath the visible chaos of stars and gas in the Antennae Galaxies, an invisible force is at work: magnetic fields, tangled and twisted like cosmic spaghetti by the collision's violent forces. These fields might not glow or emit light, but their influence is everywhere, shaping how gas moves, where stars ignite, and even the paths of entire star clusters. Normally, a galaxy's magnetic field lines run orderly and smooth, like the grooves on a vinyl record. But here, they've been knotted into a labyrinth, with pockets of intense magnetism acting like invisible walls that guide or block the flow of material. What's wild is how these fields evolved during the merger. As the galaxies first grazed past each other, their individual magnetic fields, once separate and stable, began to stretch and snap like rubber bands. Gas clouds dragging through these warped fields generated electric currents, which in turn amplified the magnetism further, creating a feedback loop of chaos. Now the galaxies are threaded with magnetic hotspots, where field lines coil into springs so tight they can push back against gravity itself, delaying star formation in some regions while accelerating it in others. Take the galaxy's starburst regions, for example. In areas where magnetic fields run perpendicular to gas flows, they act like speed bumps, slowing down collapse and stretching the birth of stars over longer timescales. But where fields align with streaming gas, they become cosmic accelerators, funneling material into dense knots that ignite stars at breakneck speeds. This duality explains why star formation in the antennae is so uneven. Some zones blaze with newborn stars while neighboring patches remain eerily dark, all because of magnetism's invisible hand. Even more fascinating are the magnetic filaments, thread-like structures spanning thousands of light years, where field lines have been combed straight by tidal forces. These act like interstellar highways, channeling gas and cosmic rays far from their origins. Some filaments glow faintly in radio waves, their particles spiraling along magnetic paths at near light speed. Others are entirely dark, detectable only when background starlight polarizes as it passes through, like sunlight filtering through polarized sunglasses. But the real mystery lies in the field's origins. While some magnetism was inherited from the original galaxies, measurements suggest it's now hundreds of times stronger than expected. One theory points to the countless supernova exploding in starburst regions, each blast sending shockwaves that tangle and amplify fields like a blender churning milk into froth. Another idea involves black hole jets injecting magnetized plasma into surrounding gas, imprinting their own fierce signatures onto the galactic material. The implications stretch far beyond the antennae. If such extreme magnetic fields are common in mergers, they could explain why some colliding galaxies produce fewer stars than predicted. Magnetism might be putting the brakes on gravity's work. Alternatively, they could help solve how galaxies build their cosmic webs of gas, with magnetic strands guiding flows that would otherwise scatter randomly. And then there's the question of permanence. When the Antennae Galaxies finally settle into one, will these twisted fields relax into a new order, or will their knots persist for billions of years, fossilized into the merged galaxy's structure? The answer could redefine how we model galaxy evolution, proving that magnetism isn't just a side effect of collisions. It's an active player sculpting the universe in ways we're only beginning to grasp. For now, every observation peels back another layer. Radio telescopes have mapped field orientations near supernova remnants, while infrared probes reveal how dust grains align with magnetic lines like compass needles. Each dataset adds to a startling realization. In the antennae's chaos, magnetism isn't just along for the ride, it's helping write the rules of the collision itself, one invisible twist at a time. The Antennae Galaxies aren't just colliding, they're erupting. Hidden within their tangled spiral arms lies a supernova factory, churning out stellar explosions at a rate that dwarfs anything in our own Milky Way. While a typical galaxy might witness 1 or 2 supernova per century, the Antennae's frenzied starburst regions produce them almost like clockwork, some years delivering multiple cataclysms in quick succession. Each blast is a cosmic forge, scattering elements heavier than iron across interstellar space: gold, platinum, uranium, seeding future generations of stars and planets with the building blocks of everything from smartphone components to human DNA. This explosion spree starts with the galaxy's most massive stars, many born during the collision itself. In the Antennae's dense stellar nurseries, stars frequently form with masses dozens of times greater than our Sun, burning through their nuclear fuel in just a few million years. When these giants finally exhaust their hydrogen, their cores collapse in milliseconds, rebounding with enough force to tear the entire star apart. The result is a type Roman II supernova, a detonation so bright it can briefly outshine its host galaxy, visible across the universe. But what's truly remarkable is how these explosions interact with their surroundings. Every supernova shockwave plows through nearby gas clouds like a bulldozer, compressing them until new stars ignite. It's a self-perpetuating cycle. Starbirth leads to more massive stars, which explode and trigger more starbirth. The antennae have turned this feedback loop into an art form, with supernova remnants overlapping like bubbles in a cosmic foam. Some regions show evidence of multiple generations of explosions, their chemical fingerprints revealing a layered history of destruction and renewal. The interstellar medium here isn't just passively absorbing these elements, it's being fundamentally transformed. Spectroscopic studies reveal pockets of gas enriched with 10 times more heavy elements than our solar system, their chemistry reshaped by successive supernova waves. Certain areas glow neon bright with oxygen and sulfur, while others harbor mysterious molecules like Buckminster fullerene, soccer ball-shaped carbon cages that might have hitched rides on stardust grains. This pollution isn't chaos, it's a necessary step in galactic evolution. Without supernova scattering these materials, rocky planets and life itself could never exist. Then there are the rarer, deadlier explosions type Ia supernova, where white dwarf stars steal mass from companions until they detonate like thermonuclear bombs. These events distribute iron in precise, predictable amounts, acting as cosmic measuring sticks for astronomers. the Antennae's merger has sparked a surge in these explosions too, as close stellar encounters send more white dwarfs careening toward their doom. Their remnants often outlive the visible blast by millennia, expanding until they merge with the general gas flow. One such bubble, catalogued as Antennae Supernova Remnant 23, spans over 300 light-years, a fossilized echo of a detonation that predated human civilization by millennia. But the supernova factory's most lasting legacy might be hidden in plain sight: the cosmic rays it generates. Every explosion accelerates protons to near light speed, creating a haze of high-energy particles that permeate the galaxies. Some escape entirely, spraying into intergalactic space like water from a shaken bottle. Others spiral along magnetic field lines for eons, eventually colliding with gas atoms to produce gamma rays, the universe's highest energy light. The Antennae's gamma-ray glow, detected by space telescopes like Fermi, is a smoking gun for this relentless particle acceleration. Ironically, this death and rebirth cycle might be the key to the galaxy's eventual rejuvenation. As the collision subsides and star formation slows, the enriched gas will settle into a new equilibrium, cooler, denser, and primed for a quieter era of stellar birth. The same explosions that tore through the Antennae's gas clouds will have made them far more fertile for the next cosmic spring. It's a reminder that even in destruction, the universe plants the seeds of what comes next. Globular clusters should be everywhere in the Antennae Galaxies, dense, glittering balls of ancient stars that orbit galactic cores like bees around a hive. Most galaxies of this size and age host thousands of them, each containing millions of stars packed into spheres just a few dozen light-years wide. But when astronomers trained their telescopes on the Antennae, they found something baffling: a severe shortage of these stellar fossils, with only a few hundred detected where there should be thousands. It's as if someone selectively erased the galaxy's oldest relics, leaving behind a mystery that challenges our understanding of galactic evolution. The leading theory points to the violence of the collision itself. Globular clusters, though sturdy, aren't indestructible. As the galaxies first grazed past each other, tidal forces could have ripped apart many clusters, scattering their stars into the tidal tails or flinging them into intergalactic space. Others might have plunged too close to the supermassive black holes at the galaxy's centers, where gravitational shear would have shredded them like tissue paper in a cyclone. Computer simulations show that mergers like this could destroy up to half a galaxy's original globular clusters, but even that doesn't fully explain the Antennae's extreme deficit. Another possibility is observational camouflage. The Antennae's starburst regions are so bright and dusty that older, fainter globular clusters might simply be drowned out by the glare. Imagine trying to spot fireflies in front of a fireworks display. Some clusters could be hiding in plain sight, their dim light overpowered by newborn stars and glowing gas. Supporting this, infrared surveys have uncovered a handful of previously hidden clusters lurking in the dust, but their numbers still fall far short of expectations. Then there's the wild card. What if the Antennae never had many globular clusters to begin with? Their progenitor galaxies might have been unusually poor in these ancient systems, perhaps because they formed in an environment where star clusters didn't assemble as efficiently. If true, this would upend assumptions about how globular clusters trace galactic ancestry, suggesting their abundance isn't always a reliable yardstick for a galaxy's past. But the plot thickens when you examine the clusters that do survive. Many show strange chemical compositions, higher concentrations of heavy elements like iron than typical globulars, hinting they might actually be younger imposters. These could be superstar clusters born during the collision itself, mimicking the appearance of ancient globulars but holding vastly different secrets. If confirmed, it would mean the Antennae are actively forging new globular-like clusters even as the old ones vanish, rewriting the rules of how these structures form. The implications stretch far beyond this single merger. If globular clusters are being destroyed or obscured at this rate, astronomers might need to recalibrate how they use these objects to measure galactic ages and histories across the universe. The Antennae's missing clusters aren't just a local oddity, they're a cosmic wake-up call, reminding us that even the oldest structures in the universe are more fragile and more mysterious than we ever imagined. While the Antennae Galaxies dazzle in visible light with their swirling arms and sparkling starbursts, their true brilliance shines in wavelengths invisible to human eyes' infrared light. The collision glows with an astonishing infrared luminosity, outshining nearly all other known merging galaxies. This isn't just a quirk of physics, it's a direct consequence of the galaxy's violent embrace, where dust and chaos conspire to transform destruction into radiant heat. The secret lies in the sheer volume of dust-fine particles of carbon and silicate created by the explosion of massive stars and stirred up by the collision. Every supernova blast grinds surrounding material into microscopic fragments, while tidal forces churn existing dust clouds into thick, swirling veils. This dust doesn't just obscure starlight, it absorbs it, soaking up ultraviolet and visible radiation like a cosmic sponge before re-emitting the energy as infrared heat. The result, a galaxy that appears relatively modest in visible light but erupts into a blazing infrared beacon when viewed through telescopes like Spitzer or JWST. But dust alone doesn't explain the extreme infrared output. Hidden behind these opaque curtains, supermassive black holes are feasting on gas at unprecedented rates, their accretion disks glowing white-hot. The surrounding dust cocoons absorb this intense radiation, heating up until it radiates persistently in the infrared. It's like wrapping a scorching light bulb in a thick blanket. The light you can't see still turns the blanket into a thermal beacon. Some regions near the galaxy's cores reach temperatures high enough to vaporize typical dust grains, suggesting the presence of exotic, heat-resistant materials forged in the furnaces of the collision. What's truly bizarre is how this infrared glow defies expectations. Based on the Antennae's star formation rate alone, models predicted far less infrared emission than observed. The discrepancy points to an unseen energy source, likely a population of deeply buried black holes or hypercompact star clusters, whose light never escapes directly but heats the dust from within. These hidden powerhouses might account for up to 40% of the total infrared luminosity, a ghostly contribution detectable only by its thermal fingerprints. The implications stretch beyond this single merger. Galaxies like the Antennae are thought to dominate the universe's total infrared output, especially in its early epochs when collisions were commonplace. By studying how dust and black holes team up to generate this radiation, astronomers gain clues about how the first galaxies lit up the cosmos not with visible starlight, but with the same smothered, heat-redirected glow we see here. And then there's the dust's ultimate fate. Over time, radiation pressure from newborn stars will blow much of it away, thinning the veil and allowing trapped light to escape. But for now, the Antennae's infrared brilliance stands as a testament to the hidden forces at work, proving that even in the darkest corners of space, energy never disappears, it just changes form. The Antennae Galaxies harbor a secret that pulses in the most energetic light known: gamma rays, the universe's ultimate siren call of violence. Unlike the visible fireworks of star formation or the radio whispers of magnetic fields, these gamma rays scream of phenomena operating at the very edge of physics, where particles reach energies no human-made collider could ever replicate. What's strange isn't just their presence, it's their intensity. The Antennae shouldn't be this luminous in gamma rays based on their star formation rate alone, yet here they are, glowing like a cosmic beacon in observations from telescopes like Fermi and Hess. At first glance, the explanation seems straightforward. Supernova, those titanic stellar explosions peppering the galaxies, accelerate protons to near light speed, turning them into cosmic rays. When these particles slam into gas atoms, they spark gamma-ray bursts like microscopic fireworks, but the numbers don't add up. The antennae's gamma-ray output is 2 to 3 times brighter than models predict, suggesting something else is pumping extra energy into the mix. One prime suspect, the galaxy's dueling supermassive black holes, whose jets might be injecting additional cosmic rays into the surrounding chaos. Imagine a particle accelerator the size of a galaxy, where shockwaves from colliding gas clouds and black hole outbursts team up to hurl protons with unimaginable force. Then there's the distribution puzzle. Gamma rays aren't evenly spread across the antennae. They cluster in hotspots that don't always align with visible starburst regions. Some correspond to areas riddled with supernova remnants, while others glow ominously near the black hole's suspected jet paths. But a few hotspots defy explanation entirely, floating in seemingly quiet zones where no known energy source exists. Could these be echoes of past black hole eruptions, their particle beams long since faded but their high-energy afterglow lingering? Or perhaps evidence of dark matter annihilations, a controversial idea where hypothetical particles collide and disintegrate into gamma rays? The most tantalizing clue comes from the gamma ray spectrum, their energy signature. Most galactic gamma rays peak at specific energies tied to known processes like pion decay from proton collisions. But the antennae spectrum shows an unusual excess at ultra-high energies, a bump that doesn't fit neatly into any existing theory. Some astrophysicists argue this could point to a new class of cosmic ray accelerators unique to merging galaxies, where turbulence and magnetic fields conspire to push particles beyond standard limits. Others speculate it's evidence of rare microquasars, stellar mass black holes with miniature jets hidden in the wreckage. What's certain is that these gamma rays aren't just a local curiosity. Galaxies like the antennae may dominate the universe's diffuse gamma-ray background, the faint glow that permeates all of space. By cracking the mystery of their excess emissions, we could unlock secrets about how cosmic rays shape galaxy evolution, how black holes influence their surroundings, and even whether dark matter leaves fingerprints in high-energy light. Every flicker of gamma radiation from the antennae is a telegram from the universe's most extreme environments, and decoding it might rewrite what we know about the forces that govern the cosmos. Amid the Antennae Galaxies' swirling chaos, some gas clouds appear to be playing tricks on astronomers moving at such extreme velocities that they mimic the behavior of objects much farther away in the universe. This redshift illusion isn't just a minor observational hiccup. It's a direct consequence of the collision's gravitational free-for-all, where gas gets flung around at speeds approaching 1% of light speed. Imagine throwing a ball so hard it seems to vanish into the distance, except here, the ball is a cloud of hydrogen spanning light years, and the thrower is the combined gravity of two galaxies tearing each other apart. The confusion arises because redshift, the stretching of light toward longer, redder wavelength, usually signals an object's distance, with more distant galaxies appearing redder as the universe expands. But in the antennae, gas clouds acquire enormous redshift simply from being hurled outward by the collision's violence, mimicking the signature of vastly more remote structures. One particular cloud, dubbed Antennae Outlier 7, shows a redshift that would normally place it billions of light years away, yet it's clearly embedded in the merger, its true motion revealed only by painstaking analysis of surrounding starlight. These rogue clouds create a nightmare for kinematic studies, which aim to map how gas moves within galaxies. Normally, astronomers assume gas follows orderly orbits around a galactic center, allowing them to reconstruct a galaxy's mass and structure. But in the antennae, the rules break down. Gas streams intersect at oblique angles, some clouds ricochet like pinballs after close encounters with black holes, and others get trapped in gravitational eddies where they loop back on themselves. The result is a velocity map that looks less like a rotating disk and more like a scribbled-on etch-a sketch. The implications stretch beyond simple measurement errors. These chaotic motions could explain why some regions of the antennae appear weirdly, missing gas. It's not gone, just moving so fast it's been misinterpreted as background noise. Other clouds exhibit blue shifts, barreling toward us at terrifying speeds as they're slingshotted by the black holes. One such cloud, detected near the northern tidal tail, races inward at over 3 million miles per hour, its trajectory bent by encounters with hidden star clusters. Untangling this mess requires more than traditional spectroscopy. Astronomers now combine radio observations of molecular gas with infrared traces of dust to track flows in 3 dimensions, revealing structures invisible to optical telescopes. The emerging picture resembles a hurricane's wind patterns, chaotic at small scales, but with broader currents hinting at underlying order. Some redshifted clouds trace back to the galaxy's initial collision, their motions fossilized records of that first gravitational encounter. Others mark where supernova shockwaves blasted gas outward like interstellar shrapnel. What's most surprising is how these rogue clouds impact future star formation. Normally, redshifted gas would be fleeing a galaxy forever, lost to intergalactic space. But in the antennae's tangled gravity well, many clouds eventually curve back, their kinetic energy dissipated by collisions with other gas streams. This means the galaxies might reclaim much of this wayward material, recycling it into future stellar generations. It's a reminder that even in apparent chaos, the universe tends toward conservation, where nothing, not even hyperactive gas clouds, truly escapes. For cosmologists, these velocity illusions carry an important lesson. Redshift alone can't always be trusted. As telescopes probe deeper into the universe, distinguishing between cosmological expansion and local motion becomes critical, especially in the early universe where galactic collisions were the norm rather than the exception. The antennae offer a nearby laboratory to refine those techniques, proving that sometimes the cosmos' greatest tricks aren't in the distances it hides, but in the motions it disguises. Tucked away in the turbulent spiral arms of the Antennae Galaxies, astronomers have uncovered celestial oddities that gleam like cosmic diamonds, carbon stars, rare giants whose atmospheres have become so saturated with carbon molecules they defy conventional stellar evolution. Unlike typical stars where oxygen dominates chemistry, these crimson-hued anomalies have flipped the script, building thick layers of carbon compounds that would make them appear pitch black if not for the faint glow of soot-like particles radiating heat from within. What makes the antennae's carbon stars exceptional isn't just their rarity, it's the collision itself that seems to have turbocharged their creation. Normally, carbon stars form when aging giants dredge up carbon from their cores through slow, steady convection over billions of years. But in the antennae's chaotic environment, the merger appears to have fast-tracked this process. As shockwaves from colliding gas clouds rattled through the galaxies, they likely triggered violent mixing in existing stars, forcing carbon-rich material to the surface centuries ahead of schedule. The evidence lies in their peculiar spectral light signatures showing not just carbon, but exotic molecules like cyanide and carbon monoxide floating in their outer layers. Some even contain traces of silicon carbide, a compound so refractory it forms microscopic crystals resembling interstellar sand. These molecular cocktails suggest the stars are experiencing hyper-efficient dredge-up, where convection operates like an industrial elevator, hauling core material upward at unprecedented rates. But here's the twist. Many of these carbon stars reside in clusters alongside much younger stars, a pairing that shouldn't exist under traditional models. One leading theory posits that the collision's gravitational jolts caused binary star systems to merge, combining a carbon-rich aging star with a younger companion. The resulting hybrid would inherit the elder's chemically enriched atmosphere while gaining a fresh lease on life from the merger's energy, essentially hitting the reset button on its evolution. Supporting this idea are observations of polluted star clusters, where interstellar gas shows traces of carbon-rich dust likely shed by these stars. In calmer galaxies, such material would disperse thinly, but the Antennae's turbulence concentrates it into dense pockets, creating carbon-enhanced neighborhoods where future stars might form with preloaded supplies of life's key element. It's a stellar recycling program on a galactic scale where death and rebirth intertwine. Yet the ultimate fate of these diamond-like stars remains uncertain. Will their carbon envelopes cool into graphite clouds, eventually cloaking them in permanent darkness? Or will the merger's ongoing upheavals strip away their sooty shrouds, exposing their cores prematurely? Every new observation peels back another layer of mystery, proving that even in a collision dominated by brute force, delicate chemical transformations can steal the spotlight. The Antennae Galaxies weren't always the chaotic wreck we see today millions of years ago. They were elegant spirals, their arms gracefully winding around luminous cores like cosmic pinwheels. But the collisions shattered that symmetry, leaving behind ghostly remnants of their former structures, phantom spiral arms that linger like echoes of a lost era. These fractured arcs, now stretched and warped by gravity, still trace the outlines of what once was, their delicate patterns visible only when astronomers peer through the chaos with infrared and radio eyes. What's haunting about these phantom arms isn't just their fading beauty, it's the way they stubbornly cling to function. Despite being torn apart, some segments continue forming stars, as if unaware their galactic foundation has crumbled. Imagine a tree branch broken in a storm, yet still sprouting leaves. These stellar nurseries persist in the most unlikely places, their newborn stars glowing defiantly against the darkness. The reason lies in the arm's original design. Spirals are density waves, regions where gas naturally compresses as it orbits. Even when distorted, those gravitational ripples can still trigger star birth, creating isolated pockets of brilliance along the ruins. Yet the arm's survival is fleeting. As the merger progresses, tidal forces pull them into ever stranger shapes, some stretched into long filaments, others coiled into chaotic loops. One particularly eerie structure, dubbed the spectral arc, curves through the northern tidal tail, its stars and gas moving in near-perfect synchrony despite being millions of light-years from their original positions. This coherence suggests the arm's underlying gravitational blueprint endures, a hidden scaffold guiding material even as the visible structure disintegrates. The most surprising detail, these phantom arms aren't just passive relics, they're still shaping the galaxy's future. Radio telescopes have detected streams of cold molecular gas flowing along their invisible spines, channeling raw material toward the merger's central starburst regions. It's as if the galaxy's original highways, though crumbling, remain the preferred routes for cosmic traffic, directing fuel to where it's needed most. This hidden infrastructure might explain why star formation hasn't run wild. The arm's lingering influence regulates the flow, preventing total chaos. But the arm's fate is sealed. Over time, their remaining gas will either be consumed by star formation or stripped away by gravitational interactions, leaving behind only scattered star clusters as tombstones. Until then, they serve as a rare window into how galaxies remember their past and how, even in destruction, the universe preserves whispers of what came before. For astronomers, these fading spirals are more than debris. They're a living lesson in the resilience of structure, proving that even the grandest designs leave ghosts behind. Among the Antennae Galaxies' most breathtaking structures are colossal cavities of hot gas, vast, shimmering bubbles that stretch far beyond the visible limits of the merging spirals. These aren't your average stellar wind creations. They're intergalactic superbubbles, some spanning tens of thousands of light-years, their surfaces rippling with energy from countless supernova and raging stellar winds. Picture a soap bubble the size of a small galaxy, its delicate shell glowing with X-rays and ultraviolet light as it expands into the void, except this bubble could swallow our entire solar system thousands of times over. What fuels these cosmic balloons? The answer lies in the concentrated fury of the Antennae starburst regions, where clusters of massive stars act like celestial sandblasters. Each star in these dense groups emits powerful wind streams of charged particles moving at millions of miles per hour. When dozens of such stars cluster together, their combined winds create a cumulative effect far greater than the sum of their parts, carving out cavities in the surrounding gas. But the real expansion comes when the most massive stars inevitably explode as supernova, their shockwaves delivering the final push that sends these bubbles ballooning outward at staggering speeds. The largest of these superbubbles, catalogued as Antennae Bubble Complex 1, extends nearly 80,000 light-years from end to end, so enormous that it dwarfs the galaxy's visible disks. Its interior is a near-perfect vacuum by interstellar standards, with gas densities millions of times lower than typical molecular clouds. This emptiness isn't passive, it's actively maintained by the relentless pressure of new supernova occurring along the bubble's edges, their explosions preventing the surrounding gas from collapsing inward. Meanwhile, the bubble's outer shell acts like a cosmic snowplow, sweeping up interstellar material and compressing it into bright, glowing ridges where new generations of stars are beginning to form. What makes the Antennae superbubbles unique is their sheer quantity and complexity. In most galaxies, astronomers might find one or two prominent bubbles here. They've mapped over a dozen major structures, some intersecting like froth in a galactic cappuccino. Radio observations reveal intricate substructures within their shells, filaments of magnetized gas, knots of dense molecular material, and even what appear to be chimneys and tunnels where hot gas escapes vertically out of the galactic plane. These features suggest the bubbles aren't just expanding uniformly, they're shaping their environments in 3 dimensions, creating intricate networks of cavities and tunnels through the interstellar medium. The long-term effects of these structures are profound. As superbubbles grow and merge, they're rewriting the galaxy's ecological maps. Some regions have become entirely disconnected from the main gas reservoirs, their star formation cut off as the last wisps of raw material are blown away. Others show evidence of triggered star formation along bubble rims, where compressed gas reaches critical density thresholds. It's a galactic feedback loop. Stars create bubbles, bubbles shape future star formation, and the cycle continues until the galaxies are left riddled with holes like cosmic Swiss cheese. Perhaps most intriguing is what happens when these bubbles burst through the galaxy's outer limits. Several superbubbles in the antennae show clear signs of blowout, where hot gas punches through the galactic disk entirely, creating fountains of material that rain back down or escape into intergalactic space forever. These eruptions may explain the presence of metal-enriched gas detected far beyond the galaxy's visible boundaries, a chemical signature of stars that lived, died, and had their remains launched into the void by these incredible structures. The Antennae superbubbles serve as a vivid reminder that galaxies aren't static paintings, they're dynamic ecosystems where stellar life and death sculpt the environment on scales almost too large to comprehend. As we study their evolution, we're glimpsing processes that likely shaped the early universe, when young galaxies blazed with star formation and filled the cosmos with bubbles of their own. Each cavity tells a story, not just of destruction, but of how the most violent events can carve out space for new beginnings. Among the many mysteries swirling through the Antennae Galaxies, one stands out as particularly audacious, a supermassive black hole that might have gone rogue. Astronomers have detected a bizarre trail of hypervelocity stars streaking through the merger's outskirts, moving with such precise alignment that they resemble cosmic breadcrumbs. The leading explanation, one of the galaxy's central black holes could have been catapulted outward during the collision, tearing stars from their orbits as it fled the scene like a celestial outlaw. The physics behind this scenario is as thrilling as it is improbable. When two supermassive black holes spiral toward merger, their final moments unleash gravitational waves so asymmetrical that the resulting recoil can kick the newborn black hole clear out of the galactic core. Think of a rifle firing a bullet backward, except here, the bullet weighs millions of suns, and the kick comes from ripples in spacetime itself. Simulations suggest these kicks could reach speeds over 3,000 miles per second, enough to overcome even a galaxy's immense gravitational pull. Yet the evidence in the antennae remains tantalizingly inconclusive. The star trail, dubbed the Phantom Path, extends nearly 60,000 light-years from the merger's core, its stars exhibiting nearly identical velocities despite originating from different regions. Normally, such coherence would require an unseen gravitational anchor, and a runaway black hole fits the bill perfectly. But without detecting the black hole directly, astronomers are left chasing shadows. The culprit could be lurking just beyond current telescope limits, shrouded in dust or stripped of its accretion disk during ejection, rendering it nearly invisible against the cosmic backdrop. Alternative explanations abound. Some researchers argue the Phantom Path could be a tidal stream debris from a devoured dwarf galaxy, while others propose it's the wake of a close encounter between two star clusters. But the runaway black hole hypothesis persists because it explains the trail's unnatural straightness and the star's extreme speeds. If confirmed, it would mark the first observational evidence of such an event at this scale, proving that even the universe's most massive objects aren't immune to gravitational eviction. The implications ripple across astrophysics. A successful escape would challenge assumptions about how black holes shape their host galaxies, suggesting some mergers might leave behind headless galaxies stripped of their central anchors. It also raises eerie questions about the black hole's fate. Would it wander the cosmic void forever, or might it eventually slow and ignite a quasar in some distant galaxy cluster? For now, the antennae keep this secret close, their phantom path standing as either a cosmic crime scene or one of nature's most elaborate illusions. Deep within the Antennae Galaxies' swirling arms, astronomers have stumbled upon a paradox: young, vibrant star clusters that shouldn't exist according to everything we know about galactic chemistry. These stellar congregations glow with the blue-white intensity of recent birth, their massive stars burning fiercely against the cosmic backdrop. Yet when scientists analyze their light signatures, they reveal something deeply puzzling. These newborn stars contain shockingly low amounts of heavy elements, far less metal than any star cluster their age has any right to possess. It's like finding a bustling modern city where every building is mysteriously constructed with Bronze Age tools. The anomaly throws a wrench into our understanding of how galaxies build and recycle their elements. Normally, each generation of stars enriches its surroundings, fusing hydrogen and helium into heavier elements like carbon, oxygen, and iron before exploding as supernova and scattering these metals into interstellar space. Over time, this process should leave newer stars increasingly metal-rich, with old, primordial stars being the only metal-poor relics. The Antennae's merger, with its frenzied star formation, ought to have accelerated this enrichment, yet these young clusters defy the trend, their chemical makeup resembling stars from the universe's infancy rather than a modern collision. One leading explanation suggests these clusters formed from gas that somehow avoided contamination, pristine pockets left over from before the galaxies first began merging. Picture two giant vats of paint colliding. Most areas would mix into new colors, but a few sheltered droplets might retain their original hue. In the Antennae's case, tidal forces during the collision could have isolated certain gas clouds, shielding them from supernova fallout long enough to collapse into these unusual stars. Supporting this, radio telescopes have detected a few such unmixed gas clouds nearby, their chemistry frozen in an earlier cosmic era. Another possibility is even more intriguing. These metal-poor clusters might have formed from gas stripped from dwarf galaxies during the merger. Small satellite galaxies often retain more primordial compositions, having experienced fewer generations of star formation. As the antennae's gravity ripped them apart, their uncontaminated gas could have been incorporated directly into new star clusters without passing through the galaxy's metal-rich crucible. Some clusters show motion patterns supporting this orbiting at odd angles that suggest external origins rather than forming from the galaxy's native material. The implications reach far beyond this single collision. Similar metal-poor young clusters have turned up in other merging galaxies, hinting this might be a universal, if rare, feature of violent galactic encounters. Their existence challenges models of chemical evolution, suggesting that mergers don't just stir galaxies' contents into uniformity, but can sometimes preserve or even reintroduce primordial conditions. It's as if the universe occasionally hits the reset button on small scales, allowing fragments of its early chemistry to persist against all odds. What makes the Antennae clusters truly special is their potential to answer one of astronomy's lingering questions: how did the first star clusters in the universe form? These modern metal-poor analogues give us a nearby laboratory to study processes that would otherwise require peering back 13 billion years. Their tight groupings mirror what we think primordial star clusters looked like, minus the mind-bending distances and faintness of truly ancient objects. By studying their structure, dynamics, and even potential planet formation, we might finally understand how the earliest stellar systems took shape in the cosmic dawn. Yet mysteries remain. Some of these clusters show internal variations, pockets of slightly higher metallicity that suggest localized pollution from recent supernova. Others appear to be actively accreting metal-rich gas from their surroundings, their strange compositions perhaps just a temporary phase. The Antennae, ever the cosmic trickster, reminds us that even its most straightforward-seeming features hide layers of complexity waiting to be uncovered. These young old star clusters stand as testament to the collision's ability to both destroy and preserve, a reminder that in the cosmic dance of creation and destruction, sometimes the most valuable treasures are the ones that refuse to follow the rules. Flowing like an ethereal halo around the chaos of the Antennae Galaxies, there's a structure that defies all expectations. A ring of debris spinning at a sharp 90-degree angle to the galaxy's main disks. Unlike the tidal tails stretching outward, this polar ring orbits perpendicularly, a celestial equator to the merger's frenzied poles. Its stars and gas move in synchronized harmony, tracing a path that suggests an entirely different origin story, one involving a lost third galaxy swallowed whole during the collision's earliest stages. The ring's existence challenges our assumptions about galactic mergers. Normally, when two spiral galaxies collide, their disks align roughly parallel, blending into a single plane over time. But the polar ring's stark orthogonal orbit hints at a dramatic encounter where a smaller galaxy, perhaps a dwarf, plunged in from an extreme angle, its material shredded and stretched into this ghostly ribbon by tidal forces. Imagine tossing a pebble into a spinning top. The debris wouldn't settle into the top's rotation, but would instead spiral outward at odd angles. That's the dynamic at play here, except scaled up to galactic proportions. What's astonishing is how coherent the ring remains despite the surrounding chaos. Infrared observations reveal it's not just scattered debris, it's a structured flow of stars, gas, and even a few surviving globular clusters, all moving together like cars on a celestial roundabout. Some sections glow with newborn stars, suggesting the ring isn't just a relic. It's an active stellar nursery fueled by gas compressed during the merger's gravitational dance. Other regions are eerily quiet, their stars old and red, possibly remnants of the original interloper galaxy's core. The ring's stability deepens the mystery. In most mergers, such off-plane structures would quickly warp or dissolve, pulled apart by the dominant galaxy's gravity. Yet this ring has persisted for hundreds of millions of years, its motion locked in a gravitational sweet spot where centrifugal force and tidal tension balance perfectly. Computer simulations suggest the original dwarf galaxy must have been remarkably dense, packed with dark matter, to anchor its debris so stubbornly against disruption. That density might also explain why the ring hasn't collapsed inward. Its dark matter skeleton could be acting as an invisible scaffold, holding the ring aloft like a cosmic hula hoop. But the real fascination lies in what the ring reveals about galactic cannibalism. The antennae were long thought to be a binary merger, but the polar ring's presence implies a more complex history. A three-body galactic interaction where the smallest player was torn apart and reconfigured into this striking formation. Its stars carry chemical signatures distinct from the main galaxies, with higher ratios of alpha elements like oxygen and magnesium, typical of smaller, faster-evolving systems. These fingerprints confirm the ring isn't just stirred-up antennae material. It's the corpse of a vanished galaxy, its essence preserved in this orbital monument. For astronomers, the ring is more than a curiosity. It's a rare chance to study dark matter distribution in 3 dimensions. By tracking how the ring's stars move, they can map the gravitational forces shaping it, revealing where dark matter clumps in the merger's outer halo. Preliminary data hints at unexpected asymmetries, with the ring wobbling slightly as if tugged by invisible concentrations of mass. Could these be dark matter substructures, remnants of the original dwarf's halo that survived the collision? Or signs of even more complex dynamics at play? The ring's future is just as intriguing. Over billions of years, it may gradually settle into the merged galaxy's plane, its material feeding new generations of stars. Or it could remain as a lasting oddity, a cosmic tattoo from the antennae's violent youth. Either way, its presence reminds us that galactic collisions aren't tidy 2-part harmonies. They're symphonies of destruction and creation, where even the smallest players can leave behind the most unexpected legacies. One of the most extreme energy hotspots in the Antennae Galaxies doesn't glow in visible light. It crackles with invisible cosmic rays, subatomic particles accelerated to nearly the speed of light. These aren't your everyday cosmic rays drifting through space. They're concentrated into blazingly intense pockets, some radiating with energies millions of times more powerful than anything produced in Earth's largest particle colliders. The source of this cosmic fury, a perfect storm of supernova explosions and black hole jets, working in tandem to turn entire regions of the galaxies into natural particle accelerators on a scale we can barely fathom. The most striking hotspot, dubbed the Northern Accelerator Complex, spans over 1,000 light-years and pulses with gamma rays, the telltale signature of cosmic rays slamming into gas atoms. Normally, such radiation would diffuse evenly across a galaxy, but here it's tightly focused, suggesting something is corralling these particles into concentrated beams. The prime suspects are the antennae's overlapping shockwaves, countless supernova, blasting outward in such rapid succession that their shock fronts collide and merge, creating a maze of magnetic tunnels that funnel particles like water through a hydroelectric dam. But supernova alone can't explain the sheer intensity. At the heart of the largest hotspot, astronomers have detected a second, even more powerful engine, a suspected microquasar, a stellar mass black hole devouring a companion star and spitting out twin jets of plasma. These jets act like cosmic bugles, blasting particles to ultra-high energies while the surrounding supernova shocks give them an extra push. The result is a multi-stage acceleration process. First, particles get a kick from the black hole's jets. Then they ricochet off supernova shock fronts, gaining more energy with each collision until they're hurled into space at nearly light speed. What makes these hotspots truly bizarre is how long they persist. Unlike short-lived supernova remnants, these regions remain active for millions of years, sustained by the antennae's endless supply of fresh explosions and black hole activity. Some show evidence of overlapping generations, older particle beams crisscrossing with newer ones, creating interference patterns in their gamma-ray emissions. It's as if the galaxies have built a natural particle collider that never powers down, constantly recharging itself with each new stellar cataclysm. The implications reach far beyond the antennae. Similar hotspots likely existed in the early universe, where galaxy collisions were common and supernova erupted like fireworks. These cosmic accelerators may have shaped the evolution of entire galaxy clusters, their rays heating interstellar gas and even influencing where new stars could form. Some theories suggest they could be the origin of the ultra-high-energy cosmic rays that occasionally strike Earth's atmosphere, particles so energetic their sources have long been a mystery. If so, the antennae offer a nearby laboratory to study processes that shaped the cosmos from its earliest epochs. Yet puzzles remain. Some hotspots emit particles with energy distributions that don't match any known astrophysical models, hinting at undiscovered acceleration mechanisms. Others appear to flicker unpredictably, as if something, perhaps clumps of dense gas drifting through the region, is intermittently blocking the particle beams. The antennae's cosmic ray factories are far from fully understood, but one thing is clear. In these turbulent pockets of space, nature has perfected the art of turning destruction into the ultimate power source, proving once again that even chaos follows rules we're only beginning to decipher. Among the Antennae Galaxies' most striking oddities are the so-called blue blobs, isolated pockets of star formation that blaze with such intense ultraviolet light they appear almost artificial against the cosmic backdrop. These aren't attached to the main galactic bodies but float freely in the tidal debris, each a self-contained island of stellar birth glowing with the blue-white brilliance of massive young stars. Some span just a few hundred light-years, yet they outshine entire star clusters in nearby galaxies, their luminosity defying logic given their diminutive size. What makes these blobs so puzzling is their origin. Unlike typical star-forming regions embedded in galactic arms, these blue anomalies seem to have formed spontaneously within collapsing gas pockets stranded during the collision. Picture two galaxies tearing past each other, their gravitational forces shredding vast clouds of hydrogen like cosmic confetti. Normally, this gas would either fall back into the merger or dissipate into the void. But in rare cases, dense knots survive the chaos, their self-gravity overcoming tidal disruption to ignite star formation in total isolation. The blob's chemistry adds another layer of intrigue. Spectroscopy reveals their metal poor compared to the galaxy's main starburst regions, suggesting they formed from gas that avoided pollution by earlier supernova. This pristine quality makes them cosmic time capsules, offering a glimpse into how stars might have formed in the early universe before heavy elements became widespread. Yet paradoxically, their stellar populations are among the youngest in the antennae, with some stars less than 5 million years old, a blink in cosmic terms. This combination of youth and chemical simplicity shouldn't coexist, challenging models of how galactic collisions redistribute and enrich gas. Their structure defies expectations, too. While most star clusters are roughly spherical, the blue blobs often exhibit irregular, filamentary shapes with tendrils of glowing gas stretching far beyond their cores. One particularly striking example, dubbed Blob Gamma 7, resembles a cosmic jellyfish, its tentacles of ionized hydrogen extending over 1,000 light-years. These filaments likely trace magnetic fields or shock fronts where stellar winds from massive stars collide with surrounding debris, sculpting the gas into eerie, elongated forms. What's equally fascinating is what the blobs lack: dark matter. Unlike dwarf galaxies, which are held together by invisible halos, these isolated star factories show no gravitational evidence of dark matter anchoring them. Their stars move solely under the influence of visible mass, meaning the blobs are essentially naked stellar nurseries unshackled from the dark scaffolding that typically governs galactic structures. This makes them natural laboratories to study star formation in its purest form, uncomplicated by the mysteries of dark matter's role. But the blobs won't last. Their massive stars burn furiously and die young, with supernova already beginning to erode some of the smaller blobs. Over time, these explosions will shred their birth clouds, dispersing material that may eventually merge with the tidal streams or fall back into the main galaxies. A few might leave behind tightly bound globular clusters as tombstones, while others will vanish without a trace, their stars scattering into the intergalactic void. These celestial oddities remind us that the universe thrives on improvisation. In the grand collision of the Antennae Galaxies, amid the carefully choreographed dance of gravity and gas, the blue blobs are cosmic jazz, unscripted, brilliant riffs of star formation that follow their own wild rhythm. And in their fleeting brilliance, they offer clues to how the universe builds stars not just in galaxies, but in the forgotten corners where no one expected them to shine. Amid the chaos of colliding stars and swirling gas, the Antennae Galaxies hide an optical trick of cosmic proportions. Their immense gravitational pull bends and magnifies light from objects far behind them, creating distorted mirages that reveal secrets about the unseen scaffolding of the universe. This phenomenon, called gravitational lensing, transforms the galaxies into colossal natural telescopes, their warped space-time crafting multiple images of distant quasars and galaxies like reflections in a funhouse mirror. The effect works because mass curves space-time. The greater the mass, the more extreme the distortion. When light from a background object passes near the antennae's combined heft, which includes not just visible stars but vast halos of dark matter, its path bends around the galaxies like a river flowing around boulders. The result, strange arcs and duplicate images of the same celestial object, often stretched into smears or ring-like shapes called Einstein rings. One particularly striking example is a lensed galaxy located nearly 8 billion light-years behind the antennae, its light warped into a perfect crescent as if stretched by an invisible hand. But these lensed images aren't just cosmic curiosities, they're precise tools for mapping the antennae's hidden dark matter. By analyzing how the background light distorts, astronomers can trace the gravity responsible for the bending, revealing where dark matter clumps most densely. Surprisingly, the lensing maps show dark matter isn't distributed smoothly but forms intricate filaments and knots, some offset from the visible galaxies altogether. These mismatches hint at complex interactions during the collision, with dark matter behaving more like an invisible fluid than originally predicted, flowing around the galaxy's cores rather than staying neatly anchored to them. What makes the antennae's lensing unique is its dynamic environment. Most gravitational lenses occur around serene galaxy clusters where mass is relatively static. Here, the ongoing merger introduces turbulence, moving clumps of dark matter and gas that cause the lensed images to flicker or shift over time. In 2019, astronomers observed one lensed quasar brighten unexpectedly, likely due to a dense dark matter substructure passing through the light path, momentarily focusing it like a magnifying glass. Such events offer rare glimpses into dark matter's granularity, suggesting it might be clumpier on small scales than current models allow. The lensing illusion also unveils the antennae's total mass with unprecedented precision. Combining the distorted arcs with measurements of stellar motion reveals the galaxy's weigh at least 50 trillion times more than our Sun, an astonishing figure where visible matter accounts for less than 10%. The rest, a shadowy dominion of dark matter, its gravitational grip sculpting not just the lensed images but the entire future of this merger. As the galaxies continue their dance, their lensing effects will evolve, offering astronomers a front-row seat to how dark matter responds when galaxies collide, a mystery that could redefine our understanding of the universe's hidden architecture. And perhaps most remarkably, some lensed objects behind the antennae are themselves galaxies from the early universe, their light amplified enough to study in detail. This cosmic magnifying glass gives us access to epochs otherwise beyond our telescope's reach, as if the collision has gifted us a portal to the distant past. The antennae's gravity doesn't just distort light, it bends time, revealing layers of cosmic history woven into a single, warped tapestry. For all its current chaos, the Antennae Galaxies collision is merely a fleeting moment in cosmic time, a fiery prelude to an inevitable future where these warring spirals will settle into a single, serene elliptical galaxy. But the transformation won't be quick or clean. Over the next several 100 million years, gravity will gradually erase the galaxy's distinctive spiral arms, smearing their stars into a smooth, football-shaped haze. The violent starbursts will fade as the remaining gas is either devoured by the central supermassive black hole or blown away by stellar winds, leaving behind a quiet giant where new stars form only rarely. What emerges from this celestial demolition derby will be fundamentally different from its predecessors. The new galaxy, sometimes called NGC 4039c in simulations, will likely swell to twice the mass of our Milky Way, its stars orbiting in random directions like a swarm of disoriented bees rather than the orderly spiral dance they once followed. The most spectacular relics of the collision, the tidal tails, the starburst regions, the hypervelocity stars, will either dissipate into intergalactic space or be gravitationally recaptured, their material recycled into the galaxy's halo. Only the tightest globular clusters and the merged supermassive black hole will remain as direct witnesses to the galaxy's violent past. The black hole's fate is particularly fascinating. Currently weighing in at roughly 50 million solar masses, it will continue growing as it consumes gas and even other black holes over billions of years. Some models suggest it could eventually rival the heftiest known supermassive black holes, reaching several billion solar masses and potentially igniting as a quasar if enough fresh gas falls inward. Remarkably, the merger's gravitational waves will still be detectable long after the galaxies blend into one, their space-time ripples encoded with the exact moment when the two black holes finally became one. Yet the collision's legacy won't end there. Chemical enrichment from countless supernova will have permanently altered the galaxy's composition, seeding it with enough heavy elements to forge rocky planets for trillions of years to come. The antennae's most enduring gift might be the carbon, oxygen, and iron now scattered through its future stellar generations, elements that could one day become part of alien oceans, mountain ranges, or even life forms. Perhaps the strangest lingering effect will be the galaxy's dark matter halo, an invisible fingerprint of the collision's violence. As the visible structures fade, computer simulations show the dark matter distribution will retain subtle asymmetries for billions of years, a ghostly reminder of how two galaxies once tore each other apart. Future civilizations, if any arise in this quieted giant, might decode these gravitational anomalies to reconstruct the epic collision that shaped their home. Time will eventually erase the antennae's fireworks, but their story will echo through the cosmos far longer than their fleeting blaze of star formation. In the grand timeline of galactic evolution, even the most violent mergers are just brief sentences in an epic narrative, one where destruction and creation endlessly intertwine. From the hypervelocity stars racing into the void to the ghostly whispers of dark matter sculpting the collision behind the scenes, the Antennae Galaxies have revealed 25 phenomena that defy expectations at every turn. These merging giants aren't just a spectacle, they're a cosmic classroom where the universe teaches us how galaxies grow, transform, and occasionally break the rules. Consider the way supernova churn out heavy elements like celestial blacksmiths, or how magnetic fields twist gas into invisible highways guiding star formation. Ponder the rogue black hole that might be fleeing the scene, trailing stars behind it like cosmic breadcrumbs. Each of these mysteries, from the metal-poor star clusters to the gamma-ray hotspots, paints a broader picture that chaos and creation are two sides of the same galactic coin. What makes the antennae truly special is how they compress universal processes into a single, observable event. Normally, astronomers piece together galactic evolution by studying countless snapshots across the cosmos, young spirals here, ancient ellipticals there. But here, we witness the entire life cycle in real time. Gas collapsing into stars, stars exploding to enrich new generations, black holes merging and reshaping their surroundings. It's as if the universe handed us a time lapse of its own workshop, revealing secrets that would otherwise take billions of years to unfold. The lessons extend far beyond this single collision. The antennae's starburst regions mirror conditions in the early universe, while their tidal tails showcase how galaxies redistribute matter across cosmic distances. Even their gravitational lensing effects, those warped mirages of distant quasars, hint at dark matter's elusive nature, offering clues that could reshape our understanding of the universe's hidden framework. Every strange phenomenon here is a puzzle piece, and together they're helping astronomers rewrite the story of how all galaxies, including our own Milky Way, came to be. Now it's your turn to join the conversation. Which of these 25 phenomena left you awestruck? Was it the cosmic ray accelerators blasting particles to near light speed, or the phantom spiral arms clinging to their past glory? Drop your favorites in the comments below, and don't hold back on suggesting future deep space mysteries we should explore next. The universe is full of wonders, and the Antennae Galaxies remind us that the more we discover, the more questions we uncover. So keep looking up, stay curious, and remember, the next cosmic revelation might be just a telescope gaze away.